first I want to thank everyone for not only staying to the last day, but also the talk right before lunch. You're all troopers, so I'll try to keep it brief for your sake. So first I'm going to go over some stuff that you've heard a lot in this section, that Proxima b has a very uncertain formation. There's three main formation pathways that could have preceded in situ formation, where it formed effectively where we see it today. It could have formed farther out in the disk and migrated inward, or it could have formed via some dynamic instability where it formed somewhere in the disk and some planet-planet scattering catapulted the planet to where it is today. And in those processes, Proxima b could be water-rich or poor today. It could have a lot of volatiles, a hydrogen envelope like Rodrigo talked about earlier, but these are things that are rather poorly constrained and need a lot of modeling. And additionally, as we heard about earlier, with no radius constraint, we can't exactly pin down what mass it is exactly. So there is still regions of parameter space, albeit unlikely from what we saw earlier, that it could have an extended hydrogen envelope and be a mini Neptune. But there's a lot of modeling that needs to be done to constrain these things. Additionally, as Rodrigo pointed out, pre-main sequence water loss in this planet is going to be very important to understand how much water exists on it today if it formed with water in the beginning. So as you can see on the right-hand side here, Proxima b, if it existed at its current orbit for its entire lifetime, existed interior to the habitable zone. I have to be careful with that. Interior to the habitable zone for around 170 million years, with some uncertainty. And during that time, as Rodrigo showed, it could have undergone some substantial water loss with, several Earth oceans, maybe up to 10 Earth oceans being lost, depending on your model parameters. Further complicating this, as we saw in an earlier talk by Rory Barnes, that tides are definitely going to be important for any M-dwarf planets residing in the habitable zone of their host stars. And these tides can tend to circularize the orbit's damp obliquities, drive tidal heating, and it can place the orbit in a tidally locked state where it could be in some flavor of a spin-orbit resonance, a 3-to-2 or a 1-to-1. Potentially. And this, as we saw earlier in GCM modeling by Tony Del Genio, can be very important for understanding what the planet looks like today, depending on its composition. So these are all very extremely important for understanding Proxima b today. So with these four physics in mind, we need to simulate these in a very cohesive framework to understand what Proxima b can be today. So the four big ones, we have tides, the evolution of the star itself, atmospheric escape, as Rodrigo talked about, and the Earth-like interior physics that can drive the formation of a core and can actually couple with these different models, especially the tidal models. So what we do is we actually couple all these physics in a framework vPlanet that's presented in Barnes et al. 2017, which is still under review. We use the tidal evolution, the constant phase lag model of Faraz Mello et al. 2008. The stellar evolution, we use Yansai-Yale tracks that are appropriate for low mass stars like Proxen. We use a 1D thermal interior code developed by Peter Driscoll and collaborators. And finally, we use the atmospheric escape formalism of Erkeev et al., which is represented also in Rodrigo's 2015 paper. Now, I want to be careful. I want to claim that we're not modeling everything in the system. As Mike Line pointed out, there's a lot of higher order physics that need to be resolved for a very robust estimation. But if we're going to simulate all these different physics to understand how Proxima b is today, and if I want to simulate all these on a PhD time scale, we have to use these 1D models in this framework so we can still come up with some robust statistical conclusions. Now, I want to say that I am committing a cardinal sin of this session. I'm not working in a Bayesian framework, but before you throw things at me, I want to mention that when you combine all these physics, this is a massive parameter space, upwards of 30 parameters. So even though vPlanet is blazingly fast, I don't care how much computer time you have, you're not going to resolve every single dimension. Now, this is stuff we're working on, but here I present some bookend end-member simulations just so we can see how these different flavors of evolution actually progress, so we can have an idea of how these different physics actually couple in reality. So first, one thing I want to note about the tides here, we work with the constant phase lag model, and that has to do with this nebulous parameter Q. And Q effectively just parameterizes how efficient the tides are, how fast the tides proceed. So on the left here, a small tidal Q is consistent with an Earth-like planet where you have these surface oceans driving very fast tidal evolutions. This is efficient dissipation. And a large tidal Q could be some planet with a very extended atmosphere, like a Neptune, let's say. So these large tidal Qs of order like 10 to the 4, let's say, lead to inefficient dissipation. So in our coupled tidal model, we effectively take the harmonic mean of the tidal Q, and if anyone wants to ask me about why that's physically justified, I'll be happy to get into that later. But effectively what we do is we include a thermal interior portion, a portion due to oceans, and an envelope in this onion planet model represented schematically below. And we simulate 3 major cases. The first one is the no ocean case, where we just have the 1D Earth model of Peter Driscoll driving the evolution of the planet. And its growth of the mantle and the internal core of the planet actually gives it a tidal Q of a few hundreds, let's say. Now in our second case, the ocean case, we just slap on an ocean of the planet, assuming a liquid surface ocean with the tidal Q consistent of Earth, which is mostly tidally driven by its oceans. And we compute the net tidal Q this way. But when the planet is in runaway greenhouse phase, there's not going to be any liquid water present on the surface. Instead, it's going to be in some steam atmosphere. So we neglect that term from our calculations. So in our final case, the envelope case, is our full onion of a planet where we have all these different terms. And we use an envelope Q of 10 to the 4 consistent with that of Neptune, derived by Zhang and Hamilton, 2008. But again, there's the caveat: when the envelope is actually present, that's going to be exerting a high pressure on the water. So it's likely going to be supercritical. So we again neglect the ocean term while the envelope is present. So now we're going to look at how some of these parameters evolve as a function of time. So here we have the tidal Q as a function of time for our cases. And note that we also have this CPL case, which is just our base case effectively, where we have a constant tidal Q of 12 through the whole simulation, just as a good reference for us. So you can see the envelope ocean and no ocean case are all dominated by this interior evolution as they all progress to a tidal Q of a few hundreds. And then you see this abrupt phase transition. And this occurs when the planet actually leaves the runaway greenhouse phase. There's some, epic monsoon where all the oceans condense, and this leads to very rapid tidal evolution as the tidal Q plummets. And we can see how this actually impacts the orbits if we look at this orbital eccentricity on the left and the semi-major axis on the right. So again, for both of these cases, you see that it's pretty much the mantle, the thermal interior, dominating this tidal evolution during the runaway greenhouse phase. And again, when you leave that phase, that's when the tides really turn on. You have this orbital circularization, and your semi-major axis starts to decay due to efficient tidal dissipation. Now we can look at tidal heating to see what goes on here. Now you see a spike, but I'll get to that. So you see initially that the no ocean case, the thermal interior, again dominates earlier. But you see this little bouncing of the envelope here. What's going on here? So what this actually is as the planet is losing hydrogen due to hydrodynamic escape, the radius actually changes. And we use some adiabat models from Eric Lopez, I believe, to actually calculate the radius as a function of hydrogen mass here. So that's what's going on for this little wiggling. Now again, as you guessed it, this spike is due to oceans condensing, the efficient tides turn on, and you get some substantial tidal heating actually, in excess of Io, which is of order 2 watts per meter squared. Now, this planet isn't going to be throwing up its guts like Io is. Instead, this tidal dissipation mostly happens at the ocean rock interface here. So this could warm the ocean, but probably not appreciably at this tidal heat flux. But for closer in planets, as the tidal forces get stronger, depending on your orbital distance to the star, you can get more substantial tidal heating in a scenario like this. And that was explored in a 2013 paper by Rory, but I won't get into that anymore. And then finally, let's look at how the hydrogen envelope on the left, that mass, and the water content on the right actually varies as a function of time. So in our 2 cases where we actually have liquid water, we have the ocean case in blue, which doesn't have the hydrogen envelope, and then the envelope case in the orange line, which does have a hydrogen envelope, hence its name. We can see that the envelope actually decreases due to this hydrodynamic escape, such that the entire envelope has been not pushed off the planet, but it's fully escaped by around 80 megayears or so. And in this time, it's interesting, if you look at the water curve, you see that that hydrogen envelope has protected the surface water in this case. And this can be, and of course, once you see the oceans condense and you leave the runaway greenhouse phase, there's no water in the atmosphere that could be subject to photolysis and subsequent escape. But if you look in this case, you can see that the hydrogen envelope can actually be very efficient in preserving some surface water. So you see it doesn't lose any when the envelope is present, and in this, obviously fine-tuned case, we end up with roughly 1 Earth ocean of water, which is excellent. Now again, like Rodrigo, I'm not going to claim to have solved Proxima Centauri b, but these are some interesting cases that must be considered for a planet like this, especially when there are large uncertainties on its formation. So I'll conclude and say that coupling these physics, like although they are 1D models and they are rather simple, but they're very important to understand the cohesive evolution of such a system, especially when there are non-zero cases that can lead to a habitable Proxima b today. As an optimist is what I hope for, albeit likely, it's unlikely. And we have this code vPlanet that allows us to couple these and simulate a large number of these, not necessarily 10 to the 40 or so, but still enough that we can do some sort of these Bayesian analyses that Rodrigo presented earlier. And of course, this depends a lot on its formation, which needs to be constrained by models in terms of how much water it has and its hydrogen envelope. And of course, this is a huge parameter space to explore. So if we are going to do any sort of Bayesian stuff with this coupled model, we have to speed it up. And I will, plug myself, of course, that this is some work I'm doing using machine learning to actually speed this up and appropriately sample high-dimensional parameter spaces. And with that, I'll be happy to take any questions before lunch.
Thank you very much, David. So yeah, we do have time for questions for those of you who are not too hungry.
You could go ahead and get your coffee early as well.
I have a question sort of for all the speakers in this that talked about this vPlanet model. Is this model eventually going to be available somehow to the community that's very interested in these type of models?
I guess that's probably more of a question for me. Yeah. So yeah, that is definitely the goal, and we are working towards that. So I can't give you a precise time frame, but hopefully within the next year or so, we'll be able to release that to the public. So we're working towards it. It's our plan.
And this is a potentially naive question. This is not my field of expertise. Can you use the known or upper limits on the eccentricity for Proxen b to back out and say whether there's an ocean or not? If there's an ocean, it should have a tidal dissipation, and you should have a circular orbit if it's very good at dissipating the orbital energy. But if it's an eccentric orbit, you can argue that there can't be much ocean.
So I think in this case, whether or not there is an ocean or not is predominantly dominated by the uncertainties on our atmospheric escape model, like as Rodrigo spoke about earlier, referencing him a lot, that there is just a substantial uncertainty with the planet's previous XeV luminosity evolution, which we do try to model. In terms of its eccentricity, as a higher eccentricity, you get more orbit average flux, right? That is not a case we probed here, but even with, if we just evolve it with an eccentricity of 0.35 and keep that constant, it's still that luminosity evolution that's driving this. Although, when you get into a framework like this, that's when we can start to split hairs and see like, okay, how much ocean do you actually need to begin with if you start in a high luminosity state? And with our CPL model, it's not strictly valid at higher eccentricities like that. We need to switch to a CTL model, for example, that can handle these higher eccentricities. But here we focused more on the low eccentricity regime.
Thank you. Thank you.
All right, any more questions? All right, well then thank you all for coming to this session. We're now going to break for lunch. Before we go, I want to remind you all to please fill out the survey form that you can get at the kiosk across from the registration desk. But let's go ahead and thank all the speakers for a great session today.